Okay, we're going to start section 8.2, which is called the law of sines. The law of sines is sometimes helpful with solving triangles that are acute or obtuse. Of course, in the last section we focused on solving right triangles. And what I mean by solving a triangle is we want to find all three of the side measurements and then all three of the angle measurements. I mentioned this in the last video. For any triangle with sides A, B, and C, the opposite angles are going to be alpha, beta, and then gamma, respectively. Okay, alpha's opposite A, beta's opposite B, gamma's opposite C. Your book is using capital letters to represent the angle measurements here. So here's the law of sines. Sine of alpha over A is equal to sine of beta over B, which is equal to sine of gamma over C. I've gone through a proof of where that law of sines is coming from. You're welcome to look at that on your own. Mostly for the sake of time here, I'm going to have us kind of focus more on using the law of sines. And so why don't we take a look at some examples here. I've mentioned the alpha is opposite A, beta is opposite B, gamma is opposite C, just here in that note. So let's look at solving some triangles. Here's an example. Okay, solve the triangle. Now remember that all three angles in any triangle add up to be 180 degrees. Okay, so if they're giving me 2 out of the 3 angles here, that third angle, alpha, would be 25 degrees, since 25 degrees plus 125 degrees plus 30 degrees would give you 180 degrees. Now, to get A and C, I can use the law of sines. Notice how I don't have a right triangle, so I don't want to be doing anything with like right triangle trig. Okay, that is, I wouldn't be getting correct answers then. Okay, if I set up the law of sines, A is opposite alpha, and I've already determined that alpha is 25 degrees. So sine of 25 degrees over A would be equal to 10 is opposite 30 degrees, so that'd be equal to sine of 30 degrees over 10. Okay, and if we solve for A, cross multiply here, A would be equal to 10 times sine of 25 degrees divided by sine of 30 degrees. And I'm getting 8.45 there. Of course, make sure that you're in degree mode. My calculator is in degree mode. I would be getting wrong answers if I'm in radian mode there. Okay. For a lot of these, you'll be rounding to 2 digits. Okay. I've noticed that your book is going to be doing that on more times than not for most of the problems. So my math lab will tell you where to round, of course. Okay, and then we need to find C. Side C is opposite the 125 degree angle, so I want to say sine of 125 degrees over C is equal to, and I got a couple of options. I could stick with the same right side of the equation as I did over here, or knowing that I found A means I could have said that this is equal to sine of 25 degrees over 8.45. I would still get, the same answer there. So now I've got to solve this for C, cross multiply, and if you go to the calculator then, 10 times sine of 125 degrees over sine of 30 degrees, I was getting roughly 16.38 with that one. Okay, here's another example. So suppose that we want to solve a triangle where A is 2, C is 1, and alpha is 120 degrees. Now, in this last problem, I already had a triangle drawn, okay, but I can't draw a triangle just, for any problem, since I have no idea what the triangle looks like, because I'm limited with the information here. But I'd like to solve the triangle, okay? So we need to find B, beta, and gamma. Now, C is 1, and C, of course, is opposite gamma. A is opposite alpha. So I'm setting up the law of sines here. Sine gamma over C, C is 1, would be equal to sine of alpha is 120 degrees divided by A is 2. If I then compute sine of 120 degrees divided by 2. That would be roughly 0.433 if you go nearest 3 digits. And then you can take sine inverse of both sides. Sine inverse of 0.433 is 25.66 degrees, or 25.7. I'm going nearest to 1 digit with that. Now a couple things. So first of all here, you want to be careful about rounding too early. Okay, it wouldn't have mattered for this problem, but in some other problems it might matter. So like I'm taking sine inverse of both sides here. Sine inverse of, sine inverse of 100 of let's see here, sine of 120 degrees divided by 2. You know, like if I were to use the exact form rather than just calling it 0.433, roughly, would give me, you know, almost the same thing. Okay, it's the same if you go to the nearest 2 digits. They're rounded, but if I were to, you know, round to the nearest like 6 digits, here'd be, you know, the more exact form. Here'd be a number that wouldn't be correct out to 6 digits. Okay, now my point with that is to just be careful about rounding anything. You know, if it's possible to have this be as exact as it possibly can, you know, I'd want to be not doing any rounding earlier. So I do see that on some of the problems. You know, a student is rounding kind of earlier than they should be, and they're, you know, they're close to the right answer, but they, you know, there's that rounding error. So, you know, my advice for these is to try to have it as exact as you possibly can until the end, where you just round to the nearest 2 digits. Okay. So gamma is 25.7 degrees. Now, it wouldn't have mattered here if we were to go nearest 1 digit, but like I said, on some other problems, like it could matter. Okay. Another thing that I got to consider on occasion is if I have more than one answer. Okay, now if I were to draw a triangle, this isn't a common angle, but if I were to draw a triangle, sine of an angle is opposite over hypotenuse, right, if I'm working with a right triangle. And if I were to have that triangle in quadrant 2, the opposite side and the hypotenuse would still be positive, right? And I've got a positive value here on the right. So I'd want to consider the possibility that this angle could produce another solution if it were flipped over into quadrant 2. Here's the pi axis, okay, or 180 degrees. If I subtract 25.7 degrees from that, using symmetry here, this angle in quadrant 2 would be 154.3 degrees. Now, that's not going to be a possibility, because if I had a, you know, one angle in this triangle be 154.3 degrees and then another angle be 120 degrees, I'm already at more than 180 degrees if I add those together, and it's not possible for the third angle to be, you know, 0 or a negative, of course. So in this case, there's only going to be one solution. Now, in the next problem, we'll see a situation where there's going to be 2 solutions. So, all right. Alpha is 120 degrees, gamma is 25.7 degrees, beta would be 34.3 degrees then. If I add all 3 of these together, I'll get 180 degrees. And so all that we have to do now is find b. We can use the law of sines again. Of course, I don't want to do anything with Pythagorean theorem, right? I don't have a right triangle. Some students will mess this up and they'll be doing stuff with Pythagorean theorem. Don't do that, okay? I should use the law of sines. That's my only option, by the way, at this point, is to use the law of sines. Beta is 34.3 degrees, roughly. So sine of 34.3 degrees divided by b would be equal to sine of 120 degrees over 2. If I cross multiply on that and then go to the calculator, b is roughly 1.3. Okay. Here's another example. So I want to solve a triangle where B is 2, C is 3, and beta is 40 degrees. Okay, well beta is opposite B, right? So I can use the law of sines and find gamma to begin. Gamma, of course, is opposite C. So I've got that set up here. Sine of 40 degrees divided by 2 would be equal to sine of gamma divided by 3. Multiply both sides by 3. 3 halves times sine of 40 degrees would be roughly 0.9642. If you then take sine inverse of both sides, sine inverse of 9642 is 74.6 is roughly what I was getting there. Now, again, I'd want to consider the possibility of maybe another triangle existing. So 74.6, that would be in quadrant 1. What if I were to flip that angle into quadrant 2? Well, if I take 180 minus 74.6, that would give me 105.4 degrees. And yeah, that's a possibility, right? Because if I had an angle that is 40 degrees and then another one that is 105.4 degrees, like I'm not above 180 degrees yet. Alpha in that case would be 34.6 degrees. Now if beta is 40 degrees and gamma is 74.6 degrees, then alpha would be 65.4 degrees, right? So there's going to be two possible triangles here to consider, two different solutions. In case 1, I've found gamma and alpha. I would just have to get A then, and I can use the law of sines a second time here. So sine of 40 degrees divided by 2 would be equal to sine of alpha is 65.4 degrees divided by A. I've got to find A, cross multiply, and then go to the calculator. You'd be getting A is roughly 2.83. In this other case, if alpha is 34.6 degrees, then the only adjustment would be, over on the numerator on the right side. You can keep the left side as is, but using the law of sines. And cross multiply that, solve for A, and you're getting A is roughly 1.77. Okay, so the point of that is just to, consider the possibility that there might be two solutions or two different kinds of triangles that'll make it work with the initial conditions there. In this problem it happened. In the previous problem it did not happen, but it's still something that we'd want to be aware of or check for. Here's another example. Okay, suppose that we want to solve the triangle where B is 4, C is 5, and beta is 95 degrees. If you use the law of sines, okay, sine of gamma is opposite C, divided by 5 could be equal to sine of 95 degrees, that's beta, divided by 4, B is opposite beta, right? And if you multiply both sides by 5, and then take sine inverse of both sides, you would get an error in your calculator. Now I'm not doing that here, I just multiplied both sides by 5. 5/4 times sine of 95 degrees is roughly 1.2452 if we go near 4 digits. We know that sine of an angle is never going to be bigger than 1 or less than -1, right? The sine curve oscillates between 1 and -1, and so the output is never going to be outside of those boundaries. So there's no value of gamma where sine of gamma is going to produce a number bigger than 1. Therefore, there is no solution to this problem. There is no triangle. Basically, there's no triangle that exists where B is 4, C is 5, and beta is 95 degrees. I had one more problem I was going to do is in the book on page 554. It's a good application problem of the law of sines. And so problem 52 is a problem that we'll look at next here. It says that the navigator of a ship at sea spots 2 lighthouses that she knows to be 3 miles apart along a straight seashore, and she determines that the angles formed between the 2 line of sight observations of the lighthouses and the line from the ship directly to the shore are 15 degrees and 35 degrees. They've got that marked in an illustration there. And the distance between P and Q, these two lighthouses here, is 3 miles. All right, so I have redrawn this picture here. Here's P and Q. Here's the ship. P and Q are 3 miles apart, and I've got the two angle measurements that were given here in accordance to the ship. And in part A of this, it says, how far is the ship from lighthouse B? Okay, lighthouse P, excuse me. I'm going to call that distance A. And the first thing that I want to do here is, basically this is going to be an application where I'm solving a triangle. Okay, I'd like to solve triangle SPQ. I'm also going to want to know side C here later on. But all right, so here I've got a 15-degree angle, and I've made like two right triangles within this bigger triangle, triangle SPQ. And the reason why we did that is because we can find angle beta and angle alpha, right? If I got like a 90-degree angle here, this other angle is 15 degrees, then beta would be 75 degrees, since all three of those angles in that right triangle would add to be 180 degrees. In this other triangle, okay, here's a right angle, here's a 35-degree angle. Alpha would have to be 55 degrees, since if I take 90 degrees plus 35 degrees plus 55 degrees, I would get 180 degrees. All right, so basically I'm able to find angle alpha and angle beta pretty much right away here. And now I want to find side A. A is opposite alpha, and I've already determined that alpha is 55 degrees. Here's a 50-degree angle. And opposite the 50-degree angle is a measurement of 3 miles. So setting up the law of sines, I'm going to want sine of 50 degrees divided by 3 equals sine of 55 degrees over A. Cross multiply that, and if you go to the calculator, then A would be roughly 3.21 miles if you go nearest 2 digits. Part B, it says, how far is the ship from lighthouse Q? Okay, so I'm calling that measurement B miles here. And again, I'll want to use the law of sines. B is opposite beta, right? And beta is 75 degrees. So sine of 75 degrees over B would be equal to, I can use the same right side of the equation as I did over here in part A. Since here's my 50-degree angle, and 3 miles is opposite the 50-degree angle. And if you cross multiply that, B is roughly 3.78 miles is what I was getting from the calculator there. Okay, part C in this then. How far is the ship from the shore? Okay, well, at this point, I have now solved triangle SPQ, right? I've got all three sides known and all three angles known. How far is the ship from the shore? I'm going to call that distance C, miles, and I've got to find that distance here. I got a couple of options. I could use the law of sines and also refer to this right triangle. That is... again, I've got two right triangles in this bigger triangle here. So let me refer to this top right triangle. Actually, in the calculation, I'm using the bottom right triangle there, and A is 3.21 miles. And A in this triangle up here is opposite 90 degrees. Okay, so sine of 90 degrees over A is 3.21. That would be equal to, C is opposite beta in this triangle. Beta is 75 degrees, so I'd want to say sine of 75 degrees over C on the other side. Of course, another option I could use is this other right triangle here. So Side C would be opposite alpha. You know, I've got a measurement B already found. Okay. So again, there's a couple of different ways I could do this here, but here's my equation set up. If I cross multiply that, sine of 90 degrees, by the way, is 1. Okay, so all you have to do here is go to the calculator and type in 3.21 times sine of 75 degrees, and you get roughly 3.1 miles is would be this distance from the ship to the shore. Okay, so that's all there is here in this section. The law of sines is really just a formula. Okay, but of course, there's applications to this, and the idea is that it applies to solving a triangle. The homework is on page 542, so be sure to look at those problems for me.